Welcome. In this chapter on real-time rendering fundamentals, we are going to take a look at performance, target frame rate NMS, the frame time, GPU and CPU, profiling basics, and the four most common performance issues, which means the draw calls, pixel and vertex shaders, translucency, and shadows. Let's start off with the target frame rate NMS. If you're new to real-time rendering, the idea of having a target frame rate might be something that you're unfamiliar with. So identify a frame rate that you want your content to run at, and then make sure that all the work that you do and all the features that you enable or disable or the render quality you're going for, everything you do contributes to achieving and maintaining that frame rate. Typical frame rates we aim for are 30 frames per second or 60 frames per second. But there's also MS. In fact, MS stands for milliseconds, and it's the unit that we rather use than frames per second. So rather than measuring performance and how the environment and the rendering is running in frames per second, we'd rather do this in MS, milliseconds. That means there is 1000 milliseconds per second. So essentially, if you have 30 frames per second, it comes down to 1 second divided by 30, or 1000 in this case, divided by 30, and that is 33.3 milliseconds per frame. That is the cost for rendering a single image. The higher that cost, the lower your frame rate. For example, at 60 FPS, 60 frames per second, the MS cost would be 16 milliseconds per frame. So the lower the MS number, the better. This is a better way of measuring performance, and this is what we tend to use through the engine and when we're in production. It's the MS values we're paying attention to, and they're much more precise than the frame rate. Now, that aside, you should also be able to identify how we can measure this in the editor. I'm going to go to the editor here, and I'm in the level performance underscore example level. This is in the folder lighting underscore rendering fundamentals finished assets. In here, in the console or the output log, you can see I have the output log here. The output log might be easiest to use. The console is a specific button on the keyboard that doesn't work unless you have a standard English keyboard. But the output log, which you can get with Windows Developer Tools output log if you don't yet have it open. And in there at the bottom you can type commands. If you were to type stat FPS, you would see the frame rate. You can, by the way, also achieve this by doing a stat show FPS there, or one of these things. That's the same thing as typing the command, but I find typing the command easier. So just to repeat this, type stat FPS and it will give you the frame rate. And you can see the frame rate has the FPS, the frames per second, but also MS, the milliseconds cost. And again, that one is more interesting usually than the FPS. While we're preparing the environment here, you should also enter this t.maxfps600 or some other large number. This removes the cap on the frame rate, because you can see I have 60 FPS right now. If I enter t.maxfps600, it'll be uncapped. I now have around 200 frames per second. If you're going to assess performance, it's usually better to uncap the frame rate, because otherwise the cap might hide the effect of what you're doing. So have the cap removed so we can properly identify how much the frame rate is changing, depending on what we're doing. Now, stat FPS aside, there is also another one called stat unit. So enter stat unit in the output log. I entered it in the console here, but same thing. And you will get more numbers underneath. In fact, these will say frame, game, draw, and GPU. So you get a whole bunch of numbers. They're all in MS as well. Frame is the entire thing. So frame is essentially the same value as that, more or less, because these two are the same. But game and GPU are the most important ones. Draw is a little bit more special. So we're going to primarily focus on game and GPU. What happens is that part of the rendering is done on the CPU, that is game. So game stands for the CPU, and part of the rendering is done on the GPU. They're essentially different threads and often even different processors. And the rendering work is divided. The CPU tends to handle everything that has to do with the position, rotation, the transforms essentially, of something in the environment and in the application. That means it's going to calculate the animations, it's going to calculate the physics, it's going to calculate a collision, it's going to calculate artificial intelligence, it's going to calculate when something is being spawned or destroyed at runtime, and so on. Everything that results in an object changing position, rotation, scale, and so on. That is calculated by the CPU. The GPU essentially handles all the actual rendering. So lighting, the rendering of the models themselves, reflections, shaders, and so on and so on. Both of these happen at the same time. And it's very crucial, if you're going to understand real-time rendering performance, how these two work together. If there would, for example, if your frame rate would be low and you're looking for more performance, you first have to identify if the bottleneck is the CPU or the GPU, because it would be pointless to optimize content on the GPU if it's the CPU holding it back. Both of these have to be in sync. So the slowest of the two, that is going to be determining your performance. And that is really crucial to understand. So identify where it's slow, because otherwise you will not be able to change your workflow or your assets or start optimizing. Right, then we should also take a look at profiling basics. So profiling basics, this is already kind of part of it. You bring up stat FPS or stat unit so you can identify the frame rate, and then there are many more commands, and this is way too much to dive into for an introductory course. But you have a lot of these stat commands, stat space, and then you have, for example, RHI. And this isn't even suggested, and it's probably not suggested in the output log either. But if you type stat RHI, and I'll type this here for you again so you can see it more clearly, then you get a list of, you get some additional information and values. In fact, another one you can type is stat scene rendering, for example. If you want to disable one of the stats, by the way, you can type it again. So you can see if I enter stat RHI again, it removes the that panel. And if I then enter stat scene rendering, I get this over here. This might need a bit more screen real estate. And here you can again see the MS cost. So it shows you how much each step takes. For example, lighting drawing takes 0.21 milliseconds. So now I know that the cost of rendering lighting is this many milliseconds per frame. And you have many more stats. It's also accessible here, top left of the viewport, stat. And then essentially all of these are the same things. You can open them up and they will show you specific stats on what's happening. Stat GPU, for example. Let me hide stat scene rendering. Because see, this is the GPU one, etc, etc. So that is a basic profiling. There's other ways of doing this too. There is a GPU profiler, and so on and so on. Bring the numbers back up, and we're back to where we were. Now, the 4 most common performance issues that you will encounter, because all of these 4 are really heavy, so you're likely to encounter them, heavy for performance, or they're also easy to do wrong. So either because of the work you do or because of the engine in itself, you're likely to encounter these 4. In this level that we were working in, we have these 4 little pots here, which are essentially examples of what we're going to talk about. And these are not in the order that are in the slides. It doesn't really matter where we start. But let's start with translucency. Translucency is very difficult to render and very expensive. Here we have a particle that renders different colored transparent planes. That's all it does. But this is really expensive right now. In fact, the frame rate, and this is why I need to turn off the cap on the frame rate, it's 200 frames per second. You can see if I go in here, it's still 200 frames per second. The issue is with building small example cases, it's kind of difficult to really see the impact of things, but they are having an impact because computers are so powerful nowadays. So what I did here is I made sure that all of these examples are configurable. If you click on the particle in the middle and then look in the properties on the right, you should see a section called Instance Parameters. Expand that and expand the first entry 0 in there. And then here it says scalar. Scalar is a value. It might not be 8 for you, but it's a certain value. Try increasing that because that's the number of particles it's spawning. Try setting that to 50 or I don't know, 150 or some huge number so you're getting a lot of planes. And then try to place the camera in the middle. You can see I'm now at 45 frames per second. If I put this to say 20, I'm now at 150 frames per second. So my frame rate went from 150 frames per second to 35 frames per second. And it's only because of this. In fact, here's the more interesting part of it. If I move away, I'm back at 160 frames per second, even though it's still rendering 250 translucent planes. So it's also the distance that impacts it. This is due to pixel shader operations, and translucency is very heavy on that. If you would go to the viewport and you would go to lit, or whatever it's set to, the third button here, might not be set to lit, it should be set to lit to properly assess these things. Then you go to optimization view modes and shader complexity. You can see it's not even red anymore, it's now solid white. You can see on the bottom here it says good, bad, extremely bad. So it's extremely bad. See, every translucent plane that gets rendered adds a layer on top of the screen, and those pixels have to be recalculated because those pixels have to blend in the translucent layer on top. And for every layer that gets added, there's more and more and more pixels that have to be recalculated again and again and again for each layer. And this very quickly makes the pixel shader expense huge. So use shader complexity and be aware with translucency it's heavy. This is also why in the distance it gets cheaper, because there are simply fewer pixels that have to be rendering those translucent planes. So there's fewer pixels to run those calculations on than there are now. And that is the difference in expense. This is pixel shader based. The same thing is true for materials. Again, this is pixel shader based. This statue, we can open up the material here for a second, has an extremely complex material. In fact, it doesn't look complex, but noise with quality 10 added several times on top of each other gives an extremely expensive material. We can see it is expensive because the stats panel, Windows stats, once this is compiled, because it's still compiling and it takes a long time because it's expensive, it's going to show us the cost, and it's going to be around 2000, I believe, in instruction count. That is the expense of materials. And you can see here, once it's compiled, 2091 instructions, that is the expense. You can see here 2, this is 2000, so halfway into this scale is about 1000 instructions. And as you get closer and closer, you can see I'm at 160 frames per second. I'll switch back to lit mode. 160 frames per second. I start going close to the surface. Performance is dropping. I'm now 90 frames per second and we're around 80-ish, 90 frames per second now. So again, the more pixels on the screen use a complex, expensive material, the bigger the impact of that complex material will be on performance. Again, pixel shader related. Then you got draw calls, which is a very interesting one. This one, if you click on the little statues here, you can configure those statues. In fact, you can see there's a static mesh assigned to it here on the right. If you click the magnify glass, it will select that one in the content browser. So I'm doing that. It's currently using this. We have 3 different statue versions. When the environment is rendered, it will render it not pixel by pixel. It will not render it block by block or region by region. It will not render it in lines or anything like that. It's going to render it object per object. If you switch to render doc here for a second, that was used earlier in these courses on rendering, then we can analyze what is being actually rendered on the GPU. This is a standalone program. It's not related to Unreal. It's about real-time rendering in general, but it can capture data from the graphical card so you can analyze it. I'm just going to switch to the unlit view here, and I'm going to show you how it actually builds up the scene. This is the rendering of the environment happening. And you can very clearly see what it does. It builds it up mesh per mesh. That's how it renders. So it slowly builds up the image, model by model. Each of those models is a draw call. So that's what a draw call is. Draw call can be a few other things too, but let's keep it simple and say every model is a draw call. And therefore the expense is not in the polygon count of the environment, but in how many draw calls you have, how many separate models are forming the environment. In this case, we have quite a lot of small statues, and you can see what would happen. If we would set the number of statues here to say 750, the frame rate went to 14 because we have many more draw calls. You can figure out what a draw call count is if you type stat RHI. And in stat RHI you can see triangles drawn, so that's the polygon count, and draw primitive calls, those are the draw calls. It's 8,400 draw calls, and you can experiment a little. So the statue with all the colors is low on polygon count, but has many different draw calls. If you open it up, you can see every one of these materials is a draw call as well, and every statue will be a draw call. So if you assign this one instead, we can see we now have 14 million triangles, but we have 26,000, 30,000, it's actually more, still going up, 40,000 draw calls. We have 10 frames per second. If I switch the exact same number of statues over to this other statue, which only has one material, but is a lot higher polygon count, is 96,000 triangles, we go from 10 frames per second to 14, 15 frames per second, and we now have 380 million triangles in view, but only 8,000 draw calls. So there's a lot more to say about this subject, but be aware that it's rendering draw call per draw call, and experiment a little by using these 3 different statues and try changing the number of models rendered, and you'll see what kind of impact it has on the performance. And then lastly, we have dynamic shadows. Dynamic shadows are really heavy. In fact, it's not the dynamic light that's heavy, it's the dynamic shadows that are heavy. It's the same kind of setup here. We have a number of statues. You can again exchange them for different types of statue. I have currently SM statue itself selected here. I have 50 statues placed. That's good enough. Let's just keep it at 50. But we can also click the lights now. So click on the lights, and all the lights were placed with scripts. So the script randomly places lights in the environment, and you can use that script to now say how many lights you want to have and whether or not the light should have shadows. See, if you turn the shadows off, I go from 70 frames per second to 100 frames per second. So it's the shadows that are making the difference, not the lights themselves. In fact, if you were to delete the lights in general, if you turn off the shadows, then delete the lights, I'm at 110 frames per second. Delete the lights, I'm at 140 frames per second. So it makes a difference, but not as big as the shadows. The best way you can test this is by assigning a very high model to the meshes on the ground. So if I take the statue called Rendering Performance 2, which has a triangle count of 96,000 triangles per mesh, and I assign that one, and we go back to the lights, and we turn on shadow casting, you can see what happens to performance. I'm 10 frames per second. So now suddenly the shadows have a huge impact on performance. In fact, dynamic shadows get heavier the higher the polygon count of the environment is. So if you intend to use a lot of dynamic shadows, you need to be more careful with the polygon count on the environment. Whereas if you're going to use only static lighting or no dynamic shadows at all, you can have a much higher polygon count. And that's clearly visible here too. If you exchange the statue to the lower poly version with the same statue, then even though the shadows are enabled, we still have very good performance. We save it around again, and it's really slow. So we've gone over target frame rate, frame time and milliseconds, frame time and GPU, CPU, profiling basics, and then the 4 most common performance issues, which is the impact of draw calls, pixel and vertex shader impact, translucency is heavy, also because of pixel shaders, and dynamic shadows are really slow, in particular if you use high polygon counts on your models.